In today's lecture, we'll be continuing with our topic of Kalman filter. So last week we have discussed the basic principle of it, and today I will repeat it so that we understand it, and we'll see a numerical example how actually is this done with some real numbers. So the Kalman filter works in two stages. The first stage is so-called prediction, and the second stage is so-called correction, or also it's called update sometimes. So in the prediction phase, we use the mathematical model that we have built in the Kalman filter to predict what will be the value of our variable and what will be the error of our prediction. So this is based on the state space model that is kind of hidden in the Kalman filter. And then when our measured variable arrived, when we have the new signal, new data comes in, we can calculate the new estimate of our variable. So the output of this correction stage will be the current estimate of our variable, updated from the last measured point, and we will get also the new error estimate. So it will tell us how do we trust the model and how do we trust the measurement. In order to do this, we need to calculate the so-called Kalman gain, which is telling us if we trust more the model or if we trust more the measurement. So this is a trade-off between the uncertainty of prediction and the uncertainty of my measured variable. So it's a trade-off between the measurement error and our error estimate that we have in the model. Kalman gain is calculated based on this equation, where the value of P is the estimate of my error of prediction, and the value R here is the measurement error. So this typically will come from a data sheet, from a sensor, and will give us info. For example, we measure temperature and the uncertainty is plus minus 3 centigrades. This is the equation that's the most important one. This equation calculates the new estimate of my variable. So my variable x depends on the previous state, which was in step x minus 1, and then it depends on the difference that we have between the measured variable, which is here shown as y, and the previous state. So if we describe this with some terminology from control systems, then this is nothing else than a p-type controller. So it acts like a p-type controller in this case. And this last equation is the estimate of my prediction error. And again, this will depend on the Kalman gain, so here the value of k, and it will depend on the previous value of the error estimate. So if we are working with a single variable, then the Kalman filter is reduced to just 3 equations like this. So let's take a look now on a numerical example. So I have taken a temperature sensor. The temperature sensor gives me some signal. That's the temperature, for example, in a room. And if I look on this output signal in the chart, it will look like this. So you have some time, and this is my measured temperature. I assume now that the temperature is constant, so let's say this would be the black line here, and this blue curve is what we will actually get from the sensor, because we have always some noise. So I will be sampling this signal x1 in some discrete time steps, and we will calculate what is the estimate based on the Kalman filter, and what is the error of this estimate and how close this goes to the real measured value. So before I begin, I need to make some estimates about the errors in my measurement and in my estimation. So let's assume that I will say, okay, I have some sensor, let's say it's for example a thermocouple, and I will have an estimate of measurement error of 1 centigrade, which is fairly reasonable. If you have a thermocouple, then this might be the error, or it might be probably something like plus minus 2 centigrades. So I have estimated that the measurement error is 1 centigrade. I will be marking the different numbers with different colors. So I will mark the measurement error in blue, which you will see then later in the table. I will mark the initial error estimate in green, and this error estimate, this is the prediction error. So I have estimated that initially I will have a larger error in my model, and I have chosen 4 centigrades. And I have also made an initial estimate of my temperature that I am looking for, and since I know that this is the sensor that measures temperature in a room, I have estimated that the initial temperature, or my initial guess, is 20 centigrades, which is, again, I think fairly reasonable, because it will be somewhere around 20 centigrades. So now here in this table I have calculated 4 different steps for 4 different samples. So I will have the first measurement that will arrive from the sensor. So this will be the first sample, and my first measurement was 24 centigrades. This is coming from the sensor, so I assuming that this is the measured value, and the measurement error is 1 centigrade. So from this I will calculate the Kalman gain, and actually I don't need this measured value in order to calculate the Kalman gain, because it does not contain the measured value, but I have chosen to put it in this table after this sample. So if we calculate the Kalman gain, we use this formula here. So we use the initial error estimate, which in my case was 4. So it's 4 divided by 4 plus 1, and 1 is the measured error. So you can see that this is this formula, and this will give me Kalman gain of 0.8. And 0.8 means that in this case I trust more the measurement, because we are close to 1 with the Kalman gain, and this means I have more confidence in my measurement. And this can also be visible from my error estimate here. I have chosen that measurement error is smaller than the error estimate of my prediction. So if this measurement error is smaller, I placed more trust in the measurement than in the model right now. Then we can use our measured value, so 24, and we can calculate the updated value of my output variable, which is based on this equation that we have over here. So 20, that's my initial estimate, because we are in first step, so this comes from the previous one, which was step 0. And 0.8 is the Kalman gain, 24 is my measured value, minus 20, that's my estimate, and this gives me 23.2. And then we will be calculating the prediction error. So here I have 1 minus the Kalman gain, so 1 minus 0.8 times the previous estimate, which was 4 centigrades, and this will give me 0.8. Then we have the second sample that will arrive, and let's say that the second sample will be 24.3. I've chosen just some random values near 24 centigrades. So again, I will calculate the Kalman gain. Now we have 0.8, which was the previous value, so this is 0.8 coming from here, divided by 0.8 plus 1. This 1 is always the same. It's the measurement error of 1 centigrade, so this will be a constant value. So this gives us 0.44 Kalman gain, and now you can see it's below 0.5. So I have a slightly larger confidence now in my model than in the measurement. If that would be 0.5, it means that I have the same confidence in the measurement and in the estimation. So you can see that already after one sample, it starts to give more confidence into the model. And then we can calculate the new update, the same value, so 23.2, that's my previous value of x, 0.44 is the Kalman gain, 24.3 that's the measured value, minus the previous estimated value, and this gives me a number like this. And then the last step would be to calculate the prediction error, so 1 minus the Kalman gain, so this is 0.44, times 0.8, which is this value, the previous value of my error estimate, and this gives me 0.45. And then we can go on with the more samples as they will arrive. But you can see here in the Kalman gain that it will go slowly to a value that is telling me that I trust the model, and I trust the model more than I trust my measurements. It will not go obviously all the way to 0, because if it would go to 0, then this would be bad. It means that it would not consider the measurements at all, and it would not update with the measured values. So in the examples I will show you, it will typically be somewhere around this value, so let's say 0.3 roughly, and this tells me that I have a little bit more confidence in the model than in the measured data. So in this table, if you go yourselves to those numbers, you will find that this is like not very difficult to understand, and if you play with the numbers, you will learn how to do this on your own. Now I have prepared a live demo, and it will be I have recorded that on video, so I will show it to you. Here I have an Arduino board, and this board has two temperature sensors. I will use only one of them to process the signal of the Kalman filter. So the way it works is that the board reads the temperature from those sensors through the bus where it's connected, and it sends the measured temperature every second through a serial line to a PC with MATLAB. And what we will see is that how will the Kalman filter react to some changes that we will have on the signal. So let me just switch to my video, and I will just run the example, and I will comment what you can see in there. So now it's sampling the signal from the sensor. You can see that it's somewhere around 23 centigrades, and that here the samples have a fairly constant value. The red stars are the actual measured temperature from the sensor without any processing, and the black stars, that's the output of my Kalman filter. And somewhere around sample 25, I will take the sensor in my hand and I will start warming it up. So we can see now how the actual data reacts. We can see that it follows the heating quite quickly, and at the same time the Kalman filter tries to follow, but the response is lagging. And we will see also today how to tune this actually, so that you have a better ability to follow this curve. But the price that we pay for this will be that we will not get such a good filtering capability. So it's always a trade-off between how good your filter is, how much noise does it suppress, and how fast can it react to the changes. So in this particular case, it would follow, it would steady itself somewhere here, but it will take more samples. And the reason for this is visible here in the table. You can see that in the table here, my Kalman gain is decreasing, and it places more and more confidence in the model. So it will have more confidence in the model, and therefore the actual measured value has not such a big weight on the update of my variable. And we'll see today how to overcome this problem and how to tune the settings of the Kalman filter. You can run this example on your own. I have posted the files in Moodle. Here is just a similar example, but with a constant signal on the input. So here I have a constant temperature, so nothing is changing. And you can see that the Kalman gain is decreasing in time. So here I have more and more confidence in the model, and I have less confidence in the measured data. And here is also the error of my estimation, so it goes along with the Kalman gain. As the Kalman gain is decreasing, we have smaller error in our estimation, and since it has a smaller error, I will place more confidence in the model and not in the measurement. Okay, so now let's take a look on how we can actually extend the Kalman filter if we will need more variables. The big advantage of the Kalman filter is that without too many changes in the algorithm, you can use it for many variables. So you can have basically variables that are in your model or in your device, but they may not be that much related. For example, if you measure acceleration, you measure angular velocity, you may measure barometric pressure, you may measure magnetic field, whatever, and you can include this very easily in a single model or a single equation with the Kalman filter. So the measured variable that we have here does not have to be a single variable, but it may be more variables. By the way, I forgot for some reason. I just on this slide I did not copy this to English, so sorry for that. I will just update this. So if we have more variables, the algorithm will change only slightly. And we will see that there are really just some few changes that we need to do if we want to make it in a matrix calculation to work with more variables. So it works still in the same way. We will have a prediction phase, and we will have a correction phase, and we will calculate the Kalman gain. But now all our equations will be with some vectors or with some matrices, and we need to adapt the equations for the matrices. So I will skip the first two equations now, and I will go to the common gain. The common gain will now be a matrix, and in this matrix we will say what is our confidence for a specific variable if we have confidence in the measurement, or if we have confidence in our estimation. So it will be exactly the same like for one variable. So in order to do this, we will need some matrix that we will be calling P. This will be the prediction of my, the error of my estimate in the previous step. And we will need also some matrix of the measurements. So this will be still the matrix R. So we can see that in mathematical terms it's mostly the same. We have some previous value of P divided by the sum of P and R. But if we want to calculate this as a matrix, we need to keep the same format of the matrices. So that's where this new matrix now called H will come in play. So let's say that the matrix A is some matrix that will help us to calculate to transfer the format of the matrix P and R into the format of matrix K. I later will show you how this looks like. It will be a matrix of ones and zeros. So this is like a simple matrix, nothing too fancy. When we have the common gain, now we can wait for the update of the measured variables. So the sensors will send us some values, we will get them and we'll calculate the new estimate of our variables. And for this, we will need to calculate the input signal, the measurement signal, and this will be again called Y here. And now the equation for the update will contain a new matrix that I will call C, and the vector xm is the vector of measurements. So now we do not put the measurement directly in this equation, but we just recalculate that into the correct format by using the matrix C, which we will again see in a minute. How does it look like? It will again be the matrix of ones and zeros. So this will be the equation that we will use to get the signals from the sensors in the same format as we will have the equation for the common gain and for the state vector x. And here is our estimation. So we calculate the new state xi, again based on the previous state xi minus 1 plus the common gain, and this is the difference between the measurement, which is hidden in y here, minus the previous state. And again note that here there's just the new matrix H, which is the same like this one, and it serves to recalculate the format of vector x into the format of the gain matrix. So from in let's say first side, this is the same equation, except we have here a new matrix that we will create a little bit later. And after we have this, the new current estimate, we will calculate the new error estimate. And again, this is the same equation like we have for one variable, except that now I is a unit matrix. So in case of one equation, we had here 1, but in case of multiple variables, this will be a matrix of ones, a diagonal matrix. We'll see it again in a minute. And since we want to keep the correct format of the matrix, we will again multiply the common gain by this H matrix and times the previous estimation. So again, this equation is virtually the same like we had before. And now let me go back to the prediction stage, where we will now have two new equations. Because in the previous case, for one variable, we really did not have the need to make any prediction here, because we did not have basically any mathematical model. We had only one variable, and why bother to make a mathematical model for one variable? So now we will fill this prediction box. We will create a new predicted state. Again, it's called xi. The reason is simple. I will use the same variables because I will first make the prediction, and then I will update it with my estimate over here in this step. And if you look at this equation, you see ax plus bu. And if you are familiar with control systems, then this is nothing else than a state space description of a system. So our new state depends on the previous state, which is hidden in the x minus y, times some matrix that I will call A, and this matrix will describe us how does the system behave in terms of dynamics. And plus the bu, and u is my input. So the current state will be influenced on the inputs through some matrix B, which will tell us what inputs do we have and how basically sensitive this system is to that. And we can add some variable that here I call W. This may represent us the noise in prediction. So you may include stuff like rounding of your numbers, finite accuracy of your calculation, and stuff like this. Anyway, in my examples, I will use this as 0, so I will not bother at all with these inaccuracies. So that's the W, and here I omitted on purpose the value of Zi, which may represent the noise of measurement, which again in my simple examples I will completely omit, so we'll not use this value of Zi and Wi. And then the second step of prediction is to calculate the prediction of my error, and this is again based on the matrix A and on the previous value of my prediction estimate. And plus q, this will be quite important, this q, because this will kind of disturb the model, the prediction, and later we'll see that the setting of the value of q will have a big influence on how well you are able to follow the actual measurement value. So how well do you trust your model, and how well do you trust your measurements? So I will show you some examples in MATLAB what happens if we change this value of q, and this will be basically the tuning factor, how well the filter will be filtering, or how well it will be following the real measured data. And since in the previous example here, in this one variable case, we did not have such a value of q, then we were not able to tune the filter and obtain this trade-off. But if you do it in this matrix version for multiple equations, then it's possible. What are the symbols that I will use in my explanation? See, I forgot to translate something. So obviously the x will be the state vector or matrix. A is a so-called transition matrix, and it is related with the dynamic behavior of the system. So it's telling me how is the system behaving if, for example, you made a transient change. B is so-called control variable matrix. So the control is my input signal u here, and this is telling me what can I change in my system, in my plant. So for example, if you let's say the system would be a temperature controller. It would be a heater. It would heat the room, for example. Then the input might be an electrical signal that you turn the heater on, you connect the current, and it starts heating. So the control variable might be electrical voltage or electrical current. C will be the so-called output matrix. We'll see later how to form that. So this is related in how we get the measured values. H will be a matrix that I will use to recalculate from format in quote marks of P to format of K, where K is the Kalman gain, and P will be the so-called process covariance matrix. Here we have the two noises. W is the predicted noise from my calculation, and Z is the measurement noise, so that is coming from the sensor. And the last three symbols here, Q, P, and R, those symbols will be matrices that will tell us something about the calculation and about the measurement. So I'll probably start with the matrix R. Matrix R is so-called sensor noise covariance matrix. And matrix R will tell us what is our trust in the measurement. So what is the variance of our signal? But it will also tell us if there is some mutual dependence between the signals from our sensors. So for example, if we would measure maybe acceleration and magnetic field of the Earth, then there will definitely be some relation between those two variables. So this will be described in the sensor noise covariance matrix. And later I will show you, today and next week, I will show you many examples how to create this matrix. The matrix P is so-called process covariance matrix. So this will tell us something about our estimation. So this will tell us what confidence do we have in our calculation, and we will use the values of matrix P and R to calculate the Kalman gain. So we will use this formula to state what is our confidence in what variable, and if we have confidence more in measurement or more in the prediction. So if we will have a larger value for the specific variable in P than in R, it means that we have more confidence in the model. On the other hand, if we will have a larger Kalman gain, that's then 0.5 for one variable in the matrix, it means that we have more confidence in the measurement hidden here in the matrix R than in the model. And the last matrix that I will call Q is the so-called process noise covariance matrix, and this is telling us something about the noise in the signal in the calculation. So by tuning the value of the matrix Q, we can give it the filter like a kind of push, so that it will not trust always the model, and for example, this will not happen. Here for this single variable I did not have this matrix Q, so as I was increasing with this number of samples, it grew more and more confident in calculation, and it did not take into account the new samples, because here the signal is not changing. And the result of this was that the signal, when there was really a change of my input signal, it did not follow very well this output signal. So this, when we change the matrix Q, we will see that it will react faster to this. Let's take a look in more detail on the meaning of the individual matrices Q and R. So the matrix Q, so-called process noise covariance matrix, has an influence on how well the signal in the Kalman filter will follow the real changes in the signal. So if you have a large value of Q, then the filter will follow better large changes in the signal. So from this point of view, it would be nice if you put the Q with a large value. But on the other hand, if you have a large value of Q, it means that it will not be able to filter out all the noise that you want to get rid of. So by tuning the value of Q, it's possible to have some trade-off between how well it filters and how well it follows. Unfortunately, the value of Q has a big impact on the numerical stability of the algorithm. So if you don't choose the value of Q correctly, it will be numerically unstable, so you may get results that are not meaningful. And what Q does it represent? Well, remember that we are creating a model, so it's some mathematical description of the reality, but the model is never perfect, so there is always some deviation between the model and the reality. So by introducing the Q value here, we say that there is really some difference between the reality and the model, and we are aware of this. So if we have a larger value of Q, we are telling, okay, I will not place that much trust in my model, but I still want that it's updated by the measurements. Because if we would have a perfect model that models exactly the reality, then we can just rely on the model and we don't need the measured data. So by introducing some value of Q that's non-zero, it will tell us that there is always something that we do not model at all. And we may call this a non-modal dynamics. So for example, you model your system as a first order dynamic system, but you know that in reality it's a much higher order. And this is the simplification that we are trying to cover in this value of Q. Now, we will see a little bit later, I think next week, how to select the value of Q so that it's fitting some exact method how to do that. Well, one of the methods. Now to the value of R. The matrix R is the sensor noise covariance matrix. So this is telling me how precise is my measurement for all the variables that I have selected. So when I have one variable which has a large value in this R matrix, then I consider that my measurement is not precise, and therefore in my calculation I will have low confidence, low weight in my selection. So obviously if I select that R has a larger value, I will place less confidence in my measurement, but on the other hand this will slow down the reaction to new samples. So exactly that's exactly what will happen here. If I have the matrix, I will have slow reaction to the update, and the filter will follow slowly. If I have a faster reaction, then it will follow nicely the input, but it will not filter that well my output signal. I think I will run the demo a little bit later so that we can see the impact of the value of Q in a minute, and I will go to some example that will tell us how we can actually get the values of the matrices A, B, and Q, and P and R in our calculation. So let's imagine the following example. We will have an object, and our object is moving. It can be, for example, a car like that. it's moving in the x direction, and so it can be in 1D, for example, but since we are in the state space, there is nothing preventing us to make it also in multiple dimensions. So for example, a drone like this, and in this case we want to find out the orientation in all three axes, so we have x, y, and z. So for this case, if I want to calculate the position and speed, the state vector x will be the speed, so the position and speed. So this is in 1D case. And in 3D case, here you can see we have x, y, and z, and then we have the corresponding speeds. So you will see that if we use this matrix equations, then the equations will always stay the same, and it's just the question, how do you define your variables here? How do you define, okay, x is this or x is that? But the algorithm itself will be exactly the same, so you don't need to change anything at all in the code. You just redefine your variables. For some cases this, for some cases that, or it might be even more complicated, but the rest of the algorithm is exactly the same. So once you have a working code, for example in MATLAB, then it's super simple to use the Kalman filter, because you just redefine the vectors and it's done, it's working. So in my example, I will focus on the simplest case, which will be this one with the car, because I just want to show you how you can actually create the matrix and how you can calculate the Kalman filter. But in my MATLAB code, you can extend it also to this drone example, and we'll see it later again. I think maybe at the end of the lecture today, or maybe next week, where I will take this example and I will extend it with more variables. So I will take the positions and speed from accelerometer, gyroscope. We will extend it with magnetometer, we'll extend it with barometer. So you will see that this vector x will have, I don't know, maybe 18 columns, and it will be like a very large variable, really complicated, but in terms of calculation it will be still our code that we will see today without any changes at all. So this is my equation that I will write right now. Here I have the previous state, I have the dynamic matrix, transition matrix A, the input matrix, and on my input signal, and this will be my noise that I have in my calculation. I will consider for all my calculations that this is 0. So now how do I create this transition matrix? Well, for this simple case, I can analyze the problem in, let's say, mathematical or mechanical description, and I can write an exact equation how this will move, because if there will be some force acting on this car, I can calculate from simple physics what will be the reaction of this car, how it will accelerate, or how fast will that move. So let's say that I have the car in here, and I want to calculate what is the current position of the car in this single coordinate x. So certainly it will depend on the initial position. So for example, I will start from 0 in my coordinate system, so from x0. Then it will depend on speed, and you can see that this is a linear motion. And then it will certainly depend on acceleration. So if there is a force that is acting on the car, it will accelerate. By the way, here I do not consider any friction at all. So in my simple calculation, if I would leave the acceleration on a constant value, now this would accelerate to infinite speed. But we will stop it very soon in time, so that this will not happen. So if you would model this like a real example, you would need to have some force that is counteracting this, which could be the friction between the wheels and the road, and it could be also the drag, the aerodynamic friction, which will increase with speed somehow. So at the end you will get a steady state where you have a balance between the force that you are applying and the, let's call it, losses that you have in the system. But in this simple example, I will not consider any losses at all, any friction. So this would be a motion with linear acceleration without any friction. So what is the input here? What do we have here? If you imagine a car like this, then obviously the input would be the torque that we have from the motor on the wheels. And this will create some force that is accelerating the car. So the input in my equation will be acceleration. So I will set that my input here is A. This will be some fixed value, for example, let's say 2 meters per second. I believe I will be using later in my calculation. So this will be a fixed value in my case. So I will use this as a motion with linear acceleration, and we'll later see how will it react if I eventually change this at some step in the calculation. And this input, this acceleration, will cause the speed changes of my car. So I initially start with position 0 and speed 0. I apply acceleration and the car starts moving forward. So in the next step I will already have some non-zero position, some non-zero speed, and I'm still applying acceleration. So I will use this formula to create, let's say, an exact mathematical model of my system. Now what's the point in using the Kalman filter if I am able to create such an exact model of my system? Well, the point is that if I use this in measurement, the measurement always comes in with some noise. So my sensor data is always noisy. So although I will have some exact mathematical description of my system, I need to filter out the input signal so that I have an estimate with a smaller error. The second reason might be that you say, okay, my object is based somehow like on this equation, because this is like a very generic equation for maybe motion of all objects. But there is something that I'm missing. There is something that I do not cover in my model. So I will use this simple model, and I will let the Kalman filter to, in quote mark, learn the dynamic behavior of my system. So in other words, it will adapt the matrix in the calculation to, let's call it, understand the system. So now we have our state vector. This is like this: speed x dot, and x is the position. How do I create the matrix A? Well, based on this equation, the matrix A is created like this. So you take this is a matrix which has ones on the diagonal, and here we have the delta t. This comes basically from this part of the equation. You can see, okay, 1 times x, this is this position x0 here, plus delta t times x dot, which is this part. So this part of the equation will give me the matrix A, and this part is my input. So this will be the b times u, and u is the acceleration, and acceleration is x with 2 dots. So I can simply create matrix A, which is here like this, a diagonal matrix. Here ones, here is 0, and here is the delta t. And delta t is my sampling period. So you see that the value of matrix A will be dependent on my chosen sampling rate. And for example, if this value of delta t is very small, I would, for example, choose that, I don't know, every nanosecond I sample the speed, then I may have numerical problems because I will have here very, very small numbers compared to the other ones. And the vector in this case, it's vector b, it's not a matrix. You can see that here I have this 1/2, that's this 1/2 times t squared, delta t squared. I have chosen that this is like sampled based, and the b times u is this b times a, like this. So it's just very simple to create those equations. Now we still are not having the Kalman filter, but so how to use this in a Kalman filter? We now need to find out what do we actually measure in our system, and what variable are we only estimating. So here in my example, I want to calculate position of the car and its speed, but I measure only its position with some noise. So with this respect, we will need to create the measurement matrix R, so that it will reflect that I do not measure the speed, but I only trust the model for this calculation. And here, if you are interested in the equation format, this is the same equation like we had for the motion, written in the variable x. So this is my current state, depends on the previous state, times this difference, plus this is the input. So this is the acceleration times this value from the matrix B. And the second equation here, this is for speed. So here I have x dot. What was the previous? What is the current speed? The current speed depends on the previous speed times accelerations times delta t. So this is still like simple physics equations. Now how do we actually form the matrices that we need for our Kalman filtering? So we will first need to understand how do we create the matrix C. And the matrix C is telling us what do we actually measure and how do we incorporate this measurement into our calculation. So for example, if I use only a sensor for position, if I measure only position, then I can choose that the matrix C looks like this. You can see 1 and 0. Why? Well, because my vector x here has this following format. I have position and speed. So if I take 1 times measured position and 0 times measured speed, because I don't measure the speed at all. So in this case, the matrix C would not be a matrix, it would be a vector, which has only one column, and it has so one row, and it has 2 columns, so 1 and 0. So this comes from measurement. If on the other hand I would measure position and speed, I can use a different format of my equation like that. C, I measure position, so in my vector y here I will have 1 times my position measurement, and then here I will have 1 times my speed measurement. So you can see that the format of the matrix C will vary based on what do we actually measure. So with the choice of matrix C, we can choose what variables do we measure and what variables we then use only in the calculation. Now about the process covariance matrix. The process covariance matrix is telling me what error do I estimate in my calculation, and it's a covariance matrix. So On the diagonal, it will have the variances of my variables, and here it will have the covariances. So here the delta x2 squared and delta yv squared, this will be the variance of my error in position, and this would be the variance in my speed. So for example, you make an estimate that you calculate the error with 5 meter accuracy, or variance here. No, sorry, no, this is not variance, this is accuracy, and this would be v squared, so that's 25. And here you calculate the error with 1 meter per second error. So here that's 1 squared, which is still 1. And here those two covariances, you may set them if you suspect that there is some relation between the two variables. So for example, if you have a combined sensor that measures speed and position, then it might be influenced by the same problems. It might be influenced by the same vibrations, by the same temperature changes, and so on. So you may put an estimate here on the correlation. If you know, or if you are certain that there is no correlation between those two signals, if it comes from independent sensors, you can set this to 0. By zeros here you say, okay, my variables are not correlated, so they are not mutually dependent. I will show you also in a calculation example what is the contribution of this covariance. It might be significant, but it might not be. So I will, in some cases, I will use zeros here in order to simplify the calculation. Okay, the last matrix before we go to the real calculation will be the sensor noise covariance matrix. And in this matrix you can select what error do you have in measurement of what variable. So I told you that I measure only position and I do not measure speed, but I have two variables. I have speed and position. Now there are basically two ways how this can be done. What you see here is that I have selected that I have some variance of my position. I have chosen that I measure the error with the position with error of 3 meters, for example. And this is the variance, so this is 3 meters, 3 squared, so it's 9. Again, it's a matrix that's typically symmetrical, so we have here the variances on the diagonal, and here you have the covariances. And here I would put the error of speed measurement. So now I have two options. Either I choose the format where I have both position and speed, and in this case I choose here some really large number. By choosing this really large number, I say fine, I may get the speed, but I don't trust it at all. So it's the same like if you don't get the speed at all. So I have chosen here just a nice round number 1000 squared. So in the effect, this will tell me that I do not have any confidence in the data about the measured speed, which I don't have. So I may produce a random signal, for example, and I measure only my position. And you can see that this choice will have an effect on the matrix H. So if I use this example where I have the 1000 squared, the matrix H, which is then used to recalculate from format of P and R to the format of K, will be a matrix like this. So it has ones on the diagonal and here zeros. So it's quite simple to create this matrix. The second approach is that I say, okay, I really measure only the position, So I will set the covariance matrix only to 9. So here this is a 3 squared. But then in this case I need a different format for the matrix H, because I will need to recalculate from the input values to my gain here. So in both cases I need to get the the gain in the same format. And for this reason, if I choose this format of R, I would need to choose a different format of H. In my opinion, it's more easy to understand if you choose the format of your matrix in the same way like you have all the other matrices, and you put here just a large number that is saying that you do not measure that. I think it's easier for more variables, because here, okay, you just put a large number and the matrix H is still the same matrix, so you just generate the matrix even for more variables which has ones on the diagonal, and that's super simple. So now that we have all the matrices, we can start calculating our Kalman gain. And the Kalman gain will tell us what confidence do we have in the calculation and measurement of position and speed. So this is the equation. I will substitute my numbers. So 25 comes from here. Here I have 1 as my estimate. So see that now I have a mistake here in my matrix. Here there should be 1 here in this position, but it will not matter at all, because I don't use this position since I have not measured the position. So sorry, I will just correct this. So there should be 1, so that it corresponds to the previous slide, and here there should be 1 as well. But at the end it will not matter at all, because it will be multiplied by divided by some very large number, so it will be 0 at the end. So we substitute this in the equation, we calculate the Kalman gain, and this is the matrix that we will get. So here we have 0.74. So this means that in my initial estimate I have more confidence in my measurement. And again, this will update in time, so it will get smaller, and I will have more confidence in my estimation. Here we have zeros, because here we have zeros in the matrices, so we're multiplying 0 by 0. And here, instead of the xxx, you can see that if I do this calculation, I'm dividing something by a very large number. So in fact, this will be 0 at the end as well. And by this 0, I say, fine, I do not trust at all my measurement, since 0 in this position of k means I trust only the model. Which makes sense, because if I do not measure it, I need to have confidence in my model and not in the measurement. So here is a numerical example how we can actually calculate, let's say, the first step of this filtering. So this is my matrix P. 25 was the position and 1 was the speed. I have chosen that my acceleration is 2 meters per second, and that my sampling period is 10 milliseconds. And here you can see my choice of the matrix R. So this is the 9, this is coming from the accuracy of my position sensor, and this large number tells me that I do not measure the speed at all. This is my matrix A. This comes from the original equation, so that this was 1 and this was delta t, which is directly this value. And here in B we had 1/2 of t squared, so this is again coming from this, and this is the value of t. And the value of u, now this is equal to a, which is the acceleration. So we do the first step in our calculation, which should be the prediction. Here you can see the equation, so matrix A, I have it, previous state of my vector, which I initially assumed that I have 0 position and 0 speed. So this is the x I when I equals to 0, and this b times u, this is b, and this is u, this is the acceleration. So I will get that the new state at time 0.01 seconds is this. So I have applied some force and it moved slightly, the position has changed, and it now has some non-zero speed. And based on this, I can make a prediction of my error. So I will use this formula. By the way, right now I did not use any value of q. I have chosen that I will have complete confidence in my model, so q is 0. And I will later show you an example in MATLAB, and we'll see what effect does it have on my model. So at the end, I will predict that this is the error of position. This is the error of speed. You can see it's almost the same like my initial guess here, 25 and 1. And in order to make it simpler, here I have, in the calculation I've put 0.01. But what you typically do is that you say, okay, I know that there is no covariance, so I will set this to 0, and I will set this to 0 as well. This will simplify and speed up our calculation a little bit later. So this is my prediction. Now I need to calculate the gain, and we've done that. Here we see, okay, gain, and here is my 0.74 number, and here is the 0, 0. So this 0 tells me that I have no confidence at all in the speed measurement because I'm not doing it. And this 0.74 tells me that now in this step I have more confidence in my measurement of speed. And now the data comes in. I have an update from the measured position, and let's say that it will tell me that measured position is 0.1 meters. And I do not measure speed, so here I will have no update at all from any speed sensor because I don't have it. So I will calculate what is the value of my inputs. Here matrix C times xm, which is the measured value. So this is this, and this is my my value of C, my matrix. It's telling how do I recalculate between the two different formats. I will calculate the new update of my state. So here we have the equation. My previous state was 0, 0. This is the Kalman gain, which I just calculated. So this is this. This is the matrix Y that's coming from here. And this is the matrix H that I have used to recalculate from the format of Y into the format of K. And at the end we'll get this. So we'll get a new update, which is telling me that this is my new position, and this is my new speed. Well, of course it's rounded here in this example. And at the end we create an equation for the new prediction error. So here we have the diagonal matrix, ones on the diagonal and zeros here outside, and we can get a prediction like this. And again, typically what you do is that you say, okay, this will be 0, this will be 0 as well, and you will just use those values on the diagonal. Well, and this repeats with the next measured value. So at the end we'll get every sample, we'll calculate all those equations, and we will get an update of our estimate. So now let's take a look on an example in MATLAB that you can try on your own. And let's say it's this one. It does not require any hardware, no Arduino, so you can just run it on your MATLAB. and it will allow me to compare the exact mathematical model that we have created here, which was this equation. This was my mathematical model with the measured data that has some noise, and we'll see how well it is able to follow the real signal. So here in my code, I am first creating the mathematical model from our equation that we've just seen, which is this one. And then if I want to employ the Kalman filter, I will use this signal and I will add some noise to it. And we can play with the noise, we can change the amplitude, we can change the type of noise, and we'll see how this will react. Then I will make the initial settings of my Kalman filter. So I need to tell what will be the format of my state vector x. What do I want to calculate? I want to calculate position and speed. I will tell what is my input variable, so in my case it's a, which is the acceleration, and I have set the acceleration to 2 meters per second. So it's like a relatively normal value if it would be like a passenger car, for example. And then I will choose the error estimates of my position and of my speed in my calculation. And I will do the same for the measurement errors. So I have set that position error is 3 and speed error is 1000, because I do not measure it, so I have used some large number. And then I define the matrices A, B, and C. So A and B, that's coming from my mathematical model. C is telling me that I measure only position and I do not measure speed at all. And then I set the process covariance matrix. So I will use the variance of my position error. You see dx squared. Here is the variance of my estimation for the speed calculation, and here I have chosen that I will use the covariance, but you can replace this with this matrix, which has zeros in place of the covariance matrix, and you will see that in this particular example it will have practically no effect. So we can try both. We can try with this one, or we can try this one. Then I have chosen the noises. So in my calculation right now, I have chosen that there is no noise in the calculation. So that's why here is Q0 and WK0 as well. We'll play with this and we'll see in the next example to see how this will affect the movement. And then I have chosen again the sensor covariance matrix. In this example, I have chosen the covariance to be non-zero, but you can see here you can set it to 0 if you know that it's independent measurement of speed and position. And again, we can see that here in this particular case it will not have that a large effect. And then in the end I just select the matrix H, which I could use some identity matrix, for example. I choose this in the value for matrix I. And then here, this is the main algorithm for the Kalman filter. So I first calculate the prediction phase. So I calculate the prediction of my process covariance matrix. I calculate the new predicted state based on what I know about the system, what I know about the matrix A and B. And then I calculate the Kalman gain. And then I wait before I have some new data. Since in my simulation I already have the data, I will not wait for it, I will just read it. And I will get it from my signal. So I will calculate the update. I will update the state from my measured value, and then I will just plot this in a chart, and I will update the prediction of my measured error. So this is a fairly simple algorithm once you understand why is it working. So you can see it's few lines of code. And if I now would solve a different problem, I just need to redefine my matrices A, B, and X, and the others. But this stays exactly the same, so I can use exactly the same algorithm, and I know that it's already working. So I will do this in future examples. I will take this code exactly to be the same, and I will just redefine the problem, and we'll run it, and we'll see that it simply works. So let me run this now, and let's see the results that we will get. So on the top chart here, you can see that this is the position versus time. So we have a motion with constant acceleration. So we're applying the acceleration on the card. It's speeding up, and it's speeding up in a linear way. So here is the speed, and you can see it's a straight line because we're applying constant acceleration. The position, if you look backwards on the equation, then it will change with a square. So here it has this shape, and the red curve here is the model. That what I got from my mathematical equations. Here it's the blue, the black stars here. That's the real signal that I get from the model without any noise. And here those black stars in the position chart, that's the signal with noise that I have just added. And the output of the Kalman filter is the blue curve in both cases. So here in this case, it's following very well, although I have like a really large noise on my signal. It has learned the dynamic behavior, and now it follows very well the model. And the same here. Basically, there is nothing to learn. This is a linear equation. So what do you want to learn? But we'll see that if I make some changes in the model that are not covered in the equation as well, then in some cases the Kalman filter will be able to follow the change as well. You can see that initially, at least for the position, it takes few samples before it adapts to the dynamic of my system. Because here I have this very small signal. I'm starting from 0, and here the speed is small, so the position changes is small. So here I see, okay, the Kalman filter is not able to estimate correctly what is my correct position, because it has a small signal and a very large noise, which is the noise is much larger than the actual signal itself. So the Kalman filter in this case is quite well able to learn the model. Now let me make some change to the system, and let's say that right now I will change the way the input is connected to my signal, to my system. So for example, between time 0 and 0.4 seconds, this will be what I have learned right now. So this will be the motion with constant acceleration. And after time 0.4, now I will remove the driving force, and it will move with constant speed. Again, I am not considering any friction, so the idea is that the car moves, and without any friction it will move with a constant speed. So how well is now the model able to adapt to this change? Because here I have basically changed the model, the behavior of the system. And you can see that it's still able to follow very well the changes. Here I have changed the dynamic behavior of the system, but here and here I have quite nice way where it follows with the speed. But in order to do this, we will need to make a slight change in the algorithm. We will need to set the value of Q matrix, because otherwise it would not follow this change. It would simply continue straight on, because it thinks that I am able to calculate it exactly, and I don't need any update from the measured value. Here in this matrix there is also an example how I can actually use this if I would measure the speed. So now I would have a sensor for position, and I would have a sensor for speed as well. Let's see the example in MATLAB. Where is it? I think it's somewhere here. So let's see what changes do we need to make if I measure the speed as well. So let's make some estimates. So let's say here I will have a sensor that measures with an error of 1 meter per second. So I have now changed this to 1, to my original number, to, let's say, my estimate, and that's all. I don't need to change anything at all, because here I have just redefined that I have some confidence in my speed measurements. And we can run it again, and we'll see that now, okay, now this is an interesting result. Now, okay, fine, that's great. Here we see that here we have some problem with the stability of our calculation. In other words, we have some numerical problem, and here you can see that it gives us like a really huge number. So that's quite a good example, a good thing that this happened. And we need to tune the algorithm a little bit so that we have some result that is believable. So first of all, let's try to remove the covariances in our matrices. So what I will do is that I will set this value of the process covariance matrix to contain only the variance of my signal, and I'll do the same for the sensor noise covariance matrix. So let's see if that will work. That will help. Yes, you can see, fine, this helped. So you can see that since we are now handling with a discrete system, with where we have finite accuracy of our calculation, then even those small numbers may be quite important. So let's see how well it follows. Here, okay, is this red curve, that's the real model. The black dots are my measured data with noise, and the blue is the Kalman filter. So okay, it's not very good because it's not following well this speed, and here we can see it on the speed estimation as well, that we have now some problem that we're not following. So it's not able to follow. It's following the dependence. It has a similar shape, but it's not fast enough. So what else can we do? We can take a look, for example, here. And here I told you that typically if I'm working with signals that are not correlated, I will use this position as 0, so I will not consider any correlation between the two signals. So I can do this in the code as well. That's here. And here I'm taking my predicted value that I've calculated, but I will erase everything that's outside of the diagonals. So I will erase everything that's not on the diagonal here, so this will be zeros. So let's see if that will have some effect. No, it does not have. Well, maybe it's a little bit better, but still it's not following perfectly my signal. So I will need to do some more update in my setting, and this update might be the value. Well, it will not by, but it will be the update here on the value of q. Because what this q is doing is that it's telling the model that it should not be that confident in the calculation, but it should trust the measurement as well. Because what this is telling us here in this chart is that, okay, I'm following the general trend that I have learned, but I'm not following the measured data. So I do not trust that much the measured data. And if we disturb this trust in the model, and we use the value of matrix Q, we'll see that it will follow more the measured data. So let's try here some small number, let's say 0.1 for example. And let's see, okay, now it got definitely better, but now we have still some noise, so we can still play with the value of Q. Let's say we will increase it, for example, I don't know, let's try 1. I think that 1 will be too much. Well, it follows quite well, but now we have more noise. So we're following the data, but here we have more noise. So as I told you on the beginning, there is a trade-off between how well will I follow the real data. By the way, here my measured data has a very large noise, so that's probably the reason why it's not following that curve quite well. But we can see that by increasing the value of Q, I kind of distort more the model, and it will follow the data more. So if you tune the model, it may give you something like this. You can see that there is a really nice following. It still follows the noise, and it follows the speed, and I have achieved this by changing the value of Q that I have in my simulation. So few examples. I think we will do this demo on the beginning of next week. I just want to tell you what is it doing. Hold on, something wrong. It should be demo here in MATLAB. And what we will see in this demo is an example from a drone. And imagine that you have only an accelerometer that measures the acceleration in 3 axes in this case. But we want to make an estimate of position, speed, and of course acceleration. So this is how the vector and the matrix will look like. It may look like super complicated, but at the end we'll use exactly the same code in MATLAB. We will only have a different definition of vector x and vector a. And I will show you this this demo on the next lecture. You can already download it from Moodle, and you can run it on your own, and you can see how it works.